Hello, everyone. Today, we're going to take a look at history of computers, and we're going to be doing that for quite some time. History is important because it tends to repeat itself, and therefore, computer history repeats itself quicker. So I was around at a very unique time, and I like to share that perspective with students because I was there during at least the 80s of the boom of the PC and how much that changed society. And so I worked during that time, right? I experienced all this myself. And I found that that really influenced what I did in my job and what I do in teaching. So regardless of what I was doing, it really gave me a perspective on, is this a fad? Is this something that's happening and I need to get on board with it? Will it change things fundamentally, or is it just a slight shift? Those kinds of things are important, unless, again, you just want to be the one that's fixing the PC or the one that's fixing the network, and somebody else makes the decisions. And that's just fine. That may be exactly what you want. Even still, this information will help you. And so I'm leading you through it and asking you to think about things along the way so you can appreciate where we came from in computers and the people that really made these phenomenal things that we now use. And also that you'll be able to see, you know, that happened back in the 50s and 60s, and it looks like it's happening again. And that very well may or will affect your job. And so as we go through this, we'll see people that, you know, for lack of a better way of putting it, lost their jobs just because they didn't see the shift. They didn't see what was happening. They didn't get on board, and they ended up, you know, getting grinded by the gears, so to speak. So we're going to start off with this document that I wrote, and this is part one of a little history. Just kind of encapsulates things, and we'll be branching out from there. So to kind of give us, you know, what are we dealing with here? I actually had students ask me, who said that? So I actually put my name on there now. Anyway, the development of the computer is one from calculator to new medium. Now, what we mean by medium is print medium. That's a newspaper. That's a book, right? Video is a medium, and the internet carries a lot of that stuff, right? It's a way to carry it. Anyway, so I want you to understand, yeah, the development of the computer is one from just being a calculator, doing numbers, to a new medium, a way to distribute information, right? A new way to present information. Certainly the computer provides a new medium, but the implementation of computing technology into every aspect of our life transcends the definition of medium. It challenges and modifies, even combines mediums of expression together. It combines communications methods. The internet is a child of the computer, which is now a channel to carry all other, if not all, mediums. So we really need to understand what I'm saying here. To boil it down, is the internet does not exist without the computer. The computer is the founding principle of having the internet function. It's the one that provides the ability to see what you're seeing on the screen. The fact that I'm here in video, that's there in type. There's also pictures. And it combines those mediums together. That's what the computer does. And the internet is the child of that computer. It wouldn't exist without it. And it's the channel that that stuff comes through. So it's kind of like you can't have the fullness of that without those two things, but you definitely can't have it without the computer. Sometimes we overlook that because we focus so much on what's coming across the internet that we don't realize the phone in our pocket, right, is a computer. And that's how we're getting our information displayed from the internet. So one of the greatest inventions in the world, you know, if you started listing out the top 5 inventions in the world, the printing press would be in the top 5, if not the first. There's lots of others, in case you're wondering, like roads, right? The airplane, all that kind of stuff. And it was invented back in 1450 and by Johannes Gutenberg, so they call it the Gutenberg. And basically the way that everything was done before, we don't, you know, think back this too far, is that everything was handwritten. So if somebody wrote down some great ideas or a great story, then that would basically have to be copied. You'd have to have, here's a page here on this side, and now I'm going to copy over here. And I'm going to copy that word for word. Hopefully I didn't make any mistakes. Next page, right? That's how it was done. Wow, that's tedious. And so information has always been power. It really has. And what happened before this time, right? That's why when you watch a lot of old movies that are supposed to date to the 1500s or 1700s or something like that, they often will show the mansion with the library, because see, that library is a manifestation of my wealth, because I'm able to have all these books, especially if you go back into the 15th century, right? So the printing press is just barely going. Then basically, right, you got a bunch of handwritten stuff that's expensive, and you're the only one, or one of the only ones, that knows that stuff, because there's only 10 copies in the whole entire world. So the printing press basically made it so that you could create a page, you could set a page, and then you could use that handle to basically imprint that on page after page after page. And of course, this is, like one of the first, or the first, I can't remember. And later on, they combined other technologies to make it so you print really fast. The printing press made it so that now you can have hundreds of books. And then once more and more people have printing presses, thousands of books. And think about it, right now, this is coming from written word and video. I've read and watched video and experienced, and that's where it came from, right? Almost everything you have comes from the written word. And that means that without that printing press, right, we wouldn't be where we are now, where basically anyone across the world that has an internet connection can look up books that were originally printed on this and read everything from them, right? So the printing press was revolutionary. And really the evolution of the computer from an idea that only a few had to each person owning more than one is not just fascinating, but it teaches us a great deal about society, about how new technology is introduced and accepted. How was this accepted and introduced? Pretty much the same way the computer was, or any other new technology. It followed the same pattern. All right, so the innovation of the computer, it predates the application of electricity. And we would, as I say here, spend a lot of time discussing that. So when you go out and say, show me a timeline of computers, this is not where most timelines begin. I begin it here, because this is when we get the first fully electronic computer. Now, we use the term electronic so much that a lot of people don't even think about what that means. That means that it's running on electricity, or therefore a flow of electrons, which becomes important for our ones and zeros later. And so this was the first fully electronic computer. I have information about Carl Zeiss. Anyway, I've got it in there, and about how he made a mechanical electrical one. And of course, there's other people that did that as well. But this is fully electronic. During World War II, that's the one I was missing, is Turing actually envisioned. So this has all been released because Turing was actually a part of trying to crack the Enigma machine. And so he was trying to basically create a computer that would do that. And his was mechanical electrical. But a big thing, right? A big visionary. He thought of a device that would be built to accomplish many tasks instead of just one. And so I put that in here because that's a fundamental shift in thinking. Usually I have this problem. I build this to fix that problem. That thing works with this. And that normally is how it functions. What he was saying, and different from everything that had been done, was we're going to build this machine, and that machine is going to be able to do many things, not just one thing. That right there is just like a crazy idea. I'm sure at the time people were just like, you're one of those really smart dudes, but you're kind of nuts, because what are you even talking about, right? It's just something that people did not think about. So he was involved in trying to crack that German code. And that's why we didn't know about that information. We knew he was a smart guy and there's a lot of writings and things, but we didn't know about a lot of that until England opened it up and said, this is what happened. But across the ocean in the US, they were building something called the ENIAC, the Electronic Numerical Integrator and Computer. And so I've got information on the guys that invented this and the women that are there in the picture for you. So you'll be looking at some of them in a little more detail. But this is the big thing, the electronic beginning. It was so great that this machine could actually do everything just with electricity. And you imagine that that's a magnitude of speed beyond what an electrical magnetical one would be. Now, just to let you know, the first term that was really applied to these was not necessarily a computer. They were called computers because they computed, right? They did math. And the term computer, as a matter of fact, you'll see this as we take a look at these couple of women and some others, is that they were computers. They were actually hired to do computing. So therefore, if your job is to sit down and compute, then you are a computer. That sounds weird to us now, right? Like we're calling them a machine. But back then it was actually calling the machine one of them. They also call them electronic brains, numerators, all sorts of different terms to try to describe what the thing would do for us. Computer is the one that's stuck. So that's what we use. That's what we use now. That's kind of transitioning to devices these days instead of computer. But anyway, in order to really understand what's going on with, okay, what does it mean to be electronic? Then we have to understand how those electrons are being used to formulate something. Now this code, this binary code, they weren't the first ones that thought of it. Carl Zeiss was also dealing with this. That was also the time of World War II. His work got cut off anyway, I'll leave that to the other video. But basically, being able to create a code, that's why it's called binary code, binary coding, binary code. So we call things coding computers these days, and that means programming computers. So coding, these days, coding is programming. Those are the same thing, exact same thing, different words, coding, programming. And coding sounds cool, and the longer you live, the more you'll see that kind of thing change. I don't know what we'll call it in 20 years from now. There'll be some other term. Maybe they'll go back to programming because that's like retro cool. I don't know. But in any case, a code is just basically, for instance, we sit down and you had to do these in school. Some people didn't, but they had these blocks up here that you would actually put these letters in, and then there was a number above it. Then you had to figure out which letter was that number in order to decipher what that was. That's a code. That's basically saying that I'm going to take 3 ones, and those 3 ones, when you read them, stands for an A. So it's a representation. That's what it is. What they did then was use the most basic 2 positions, 1 or a 0. That's the bi. 2 positions in binary. And the reason I discuss it in 100 is that we really don't discuss this too much. And it's kind of the founding principle of how everything works. Anyway, so, this is kind of an oversimplification, but basically what you can do is take a look at what these machines were built out of, which was vacuum tubes. And you can think of them like a light switch. They're either on or off. And so if it's got electrons or a flow and it's on, then it's a 1. And if it has no electrons, no flow, then it's off. Now, usually that was this kind of flow as opposed to a lower flow, not an on-off usually, but we describe it that way. And so I pulled up this information, which is really the first way of translating binary and making it represent our language. And it was called ASCII, American Standard Code for Information Interchange. So we don't use it anymore. You can look at what's being used now, but basically, if you're pulling information off of a website, how is it getting these words? What's that coming from? Well, way down, all the way down to the CPU level, it has to have 1s and 0s. That's what it has to deal with. So there's a representation of each of these as a set of 1s and 0s. And there's basically something pre that basically says, hey, this coming through is going to be ASCII. Right? So in any case, so if you had a 0, that is 0, 0, 1, 1, 0, 0, 0, 0. So you got 1, 1, 2, 3, 4, 5, 6, 7, 8. Right? That's where we get these 8s, 16, 32s, 64s, 128s. It comes down this far. We have 2 positions. Now let's actually put 2 positions in each one of these spaces. And now we can represent something. So 1 nibble, right? 1 nibble second 4 bits equals 1 nibble, right? So we've got a nibble, and 2 nibbles is a byte, right? So we got a byte of information. So if you want to represent an E, that is 0, 1, 0, 0, 0, 1, 0, 1. If you want to, right, you can actually go out on the internet and you can dump in text and say, convert this to binary, and it'll convert it for you. It'll show you what it is in binary. All right, so that's what I'm explaining here. You should read that. And here's some vacuum tubes. This was a nice picture of some old vacuum tubes, and you really can't tell scale here, right? They need a quarter or something over here in the corner so you can see. But that's basically, let's say, this one fits in your hand, the palm of your hand, right? So they were big. Back then they were really big. So if we come back up here, all of these things right here could be pulled out, and behind them is all these vacuum tubes you can barely see. There's probably one right there. And so these were banks of vacuum tubes, and you can look that up. You can actually find that on the internet. And that's the way you were going to process information, store information, and do that kind of thing. I've got some vacuum tubes that I show you in shrinking it down, and they're about that big. You know, they're much tinier, and that kind of stuff is still used, but definitely they were huge back then. And that's why a computer like this was doing very little, but man, it took up some space, right? It was room full of computers. And this is actually where they're creating the logic, right? So if I need to calculate this formula, I'm going to send it here, 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 and here, and then that'll equal this. Right? So these people had to know math like you wouldn't believe, and they couldn't use a calculator because that didn't exist. So they're actually creating the logic as they're plugging these in. In other words, they're programming this machine. There's no software programming. There's no, let me type this in, print this, that, or the other. If you're in programming and learning it or know a little bit about it, you programmed it by where these cables are going. That's how you programmed it. Could run one program, then you'd have to start over. Anyway, so then we move to transistors, tubes to transistors. And this transistor, right, that's about that big. It's actually quite a big transistor. You can get them about this big. They're super tiny. Let me see, get that right up on the camera. Really tiny. That one's about that big, and the other one's about this big. What is this thing doing? The same thing as these. So you're talking about a 40 times less the size, right? Or maybe 80, depending on what you're doing. And so you're basically saying, we can do the same thing with that transistor that we can with the vacuum tube. So no more vacuum tubes, let's just use these transistors. So that's shrinking it down. And so that's another picture of one, obviously, that's huge, but that's one of the really tiny ones. I have some of those in my office. And then breaking the tyranny. You will watch a video that talks about this. But basically what happened was, by the time they had these transistors and understanding how a computer was built, so you're talking about moving from the 40s into the 50s, so you got about 10 years of time, they began to understand, how can we make these computers do stuff that we never imagined? Let's have it do these kinds of calculations automatically when it sees this, or let's have it actually take these sets of numbers and do this with it, and it'll all be automatic. And they could design that by putting transistors where they needed them and then routing the information to those transistors. So each one of these would have, you know, basically an little electric line running from it to the next one or whatever. Well, what that really caused is that, because you're trying to do multiple things, right? Not just create a thing that does one thing over and over again. That's useless. We just spent $1 million and all it does is this one formula. You had to wire these transistors to multiple locations. So you might have one transistor going to 50 different locations. How do you wire that? So they began to really develop, and on paper, the logic of a computer that is powerful. However, they couldn't make it happen because of a wiring problem. So Jack Kilby, Texas Instruments, Robert Noyce, working for Fairchild, they both actually found a way to create what they called an IC, or an integrated circuit. Now, it's accepted as fact that Robert Noyce actually created the first one, and Jack was close behind. For years, they always said that Jack did it, and then Robert did it, and then some people would say, oh, they both did it at the same time. But now they know, according to facts, that Robert did it first, but you're talking, I think it was days. Anyway, so really what you're talking about is create a process where you can take a ton of these transistors, a lot of them, let's just say right now 100 of these, and build it into this integrated circuit, or what we would call a chip. Right. And so the first one of these was really expensive. And this is a picture of the first one. That's an early integrated circuit. Well, no, that's not the first one. One of the first 10, probably. And they created a process that enabled them to design a chip, or these circuits, and then reproduce it and reproduce it and reproduce it and reproduce it identically. You see where I'm going with this? So all of a sudden, we don't have to plug this in or this in and then run all these wires between them. We can integrate all of that onto this, which is why they call it integrated circuits, right? Or an IC. And that's still the proper term, that when you have a computer chip and you look on a motherboard and there's all these little chips all over, when you take 118, 180, you see all those little chips all over. Those are all ICs, they're integrated circuits. So that meant that through this process, you could use the functions of transistors and wire it all on one thing. It's fantastic. That's what we're at. This is not now, right? This is, some probably still looks like that, but that's one from 10, 15 years ago. And so these integrated circuits, this process, as you can imagine, brand new, was super, super expensive. So even though it solved this tyranny of numbers, and again, the tyranny of numbers just really refers to the fact that you have this little tiny transistor that's plugged in here, and another one here, and another one here, and another one here, and they have to be routed with electricity somehow. And this one needs to go to 30 over here, and this one, and then that one has to go to 15 over here, and this one and that one. And it's just too much. It's just too much wiring. And that's the tyranny of numbers. In other words, we can't do it. We can logically design it. We can't physically make it. Now with this, you can physically make it. They're like $1,000 for one of these. It's expensive. New technology is always expensive. And so there really wasn't a use for it until, so for 2 years, almost no one used any ICs. And I'm sure at universities, they buy maybe a couple and play around with it. But the machines they had were doing what they wanted. And so why would you spend the extra cash, right? But NASA actually needed a small computer to use in a small spacecraft. So a lot of people actually believe that the moon didn't happen, that people didn't go there. And it's kind of silly because they left equipment up there you can bounce lasers off of. They do that on the mountain to actually help culminate it, like every month or 3 months or something. They shoot lasers at the moon that are reflected back because of equipment that was left there. And this is a whole reason why you should believe that we went to the moon. Why would you go to all the trouble to make this small, really expensive computer that actually never would get used? You just pretend like you did it. So NASA needed this. That actually ended up in the moon lander. And of course, gosh, we got to blow stuff up. So we need to put them in the missiles, the nuclear missiles, and help them be guided. Right? This is like a first time that you could not just use analog technology for the missile to try to figure out where it was, but you could actually have a computer doing that because it's small enough to do it. And of course, they were also used in jets to help control these high-powered jets. So the original computer used to go to the moon had less processing power and electronics found in a common USB flash drive today. Now, we don't really think of what a flash drive is doing, but you've got the memory storage in the flash drive, and then basically you have a little tiny controller chip, and that's the thing telling Windows or Mac, hi, I'm a USB, whatever, this is how fast I can go, and this is how much storage I have. And it controls that flow in and out, or helps control it. And so there's actually more computing and electronics found on those flash drives today than what they landed somebody on the moon with, which is incredible. If you ever watch any of the old stuff and they're pushing those buttons, you can start to recognize hex and different commands that they're actually typing into it as they program it to do something. All right, so this becomes the electronic printing press. That's why we talked about the books. The fact that basically we got the computers to a point where somebody doesn't have to sit down and wire them all, every single one of them, and then sell that computer. They could just say, what's the design of that chip? And then make 1 million of them, right? Design once, make 1 million. And that tremendously reduced the cost. And so in 1960, the first IC had fewer than 10 transistors on it, but come on. 10 transistors at that size, that's incredible. And it cost $1,000. And then 10 years later, the cost of making an IC had dropped to pennies and were 1,000 times more powerful than what this was. So in other words, you're dealing with thousands of transistors on there already, right? So the current integrated circuits, or what we might call a processor, now have more than 700 million transistors. As a matter of fact, that's a big deal with the Apple M1, and it's got something like 16 billion transistors on it, or something like that. We'll look at it some other time. But it's just amazing. So it doesn't quite work out this way, but again, the more transistors you're putting in there, the more ability you have to compute, making the thing more powerful in computing and how it performs. So by the 70s, you had all these integrated circuits that were available, and they're pretty much sitting on shelves. So you have these components where it's being used in different equipment, wherever. But since the company that makes it can just keep making them, right? They got it, boom, boom, boom. Let's just make 1 million of them. Now I can sell them for whatever, whatever somebody wants to do with it. As a matter of fact, you could, design your own and take it to one of those places and say, hey, can you make one for me, right? Not for pennies, but you could do it. The point is that by the time we hit the 70s, you end up with a ton of components sitting there for people to start playing with and doing something with. And that is an interesting process. That's an interesting thing. And we're going to stop there, and I'll start up another video. So thanks for watching this one, and make sure you can pass that test.